Yes.
Yeah.
Yes.
Okay, so welcome all. Yuval will speak about competitive erosion. It is conformally invariant. About competitive erosion, which is invariant, conformally invariant.
Okay. Thank you. So I'll come back to this video. Tell you what the process is. So in this process we have a blue source on one side of a domain, a red source on the other side, and they alternate producing particles of their color. Now when a blue particle comes out, it moves until it reaches a red vertex, and then it turns it blue, and then you reverse the roles. I'll say this more slowly in the slides and come back to this later. So okay, so let's start this. So so what I'll describe today is joint work with Shishendu Ganguly, but a part of it is also joint with Lionel Levine and Jim Prop, and the model is due to Jim Prop, as I'll explain later. Okay, so all right, so first, happy birthday, Greg. You'll see the connection to Greg's work in a few minutes. So what is the model? It's a two-type competing system. It takes place on a finite graph with two marked sources, or more generally, two source measures. So mu1 will be a measure where the blue particles are produced, and mu2 is the measure where the red particles are produced. So we'll see how that comes in. And we'll use these to define a Markov chain on the space of subsets of a fixed size of our graph. Okay, so let me show this in a picture. So here is a very small graph with two sources. Here is the blue source marked here, the red source is marked here, and initially we have three light blue vertices, three light red or orange vertices. Now a blue particle emerges from the blue source and walks until it reaches a red vertex, and it turns it blue. So in this case it happened in one step. Let me review it. One step it moved left and reached a red vertex, so that vertex turns blue. Now it's the red source's turn, so a particle gets emitted from the red source, walks. It first walked here to this already red vertex, or light red, so it keeps going and takes another random walk step. In this case, one more step sufficed for it to reach a light blue vertex, and then it turns that vertex red. So altogether we started with this configuration of three blue vertices, and we ended after these two rounds again with the same number. So there's conservation of mass here, three blue vertices in this configuration. Each time in each round one red vertex turns blue, and then one blue vertex turns red, so we have this conservation. So this is the Markov chain on subsets of a fixed size of the given graph, and here the source measures were Dirac measures, but you could have any measure for producing a blue particle that starts moving. Okay, so again, now that you've seen it, so this is the formal definition. S at times t plus 1 is S of t union with the endpoint of a blue walk but you reduce the endpoint of the red walk, and this is the new blue set after one step. And this model was proposed by Jim Prof in 2003, motivated by internal DLA, and I'll explain that in a moment. Okay, so to understand this model, we should go back to an earlier model which has some similar features but no competition. So we have just one type of particle and a growing set. So I of t is the set at time t, and it grows by just letting a random walk start at a fixed site or according to some fixed measure and walk until it exits the current set, and that's it plus 1. So this was first proposed by Meakin and Deutsch, and then generalized by Diaconis and Fulton in 91. So here is again the model. We have each time we start at we start at the center, and we take a random walk step until we exit the current set. Okay, so this is just 4 steps of that. So it's usually studied on an infinite graph, like an infinite lattice, and then the interesting questions are what is the asymptotic shape and the fluctuations at the boundary. Here is how a typical cluster would look like after a short time, and this is a zoom on a piece of the boundary. So competitive erosion is naturally defined on a finite graph, and so there we will ask different questions about, coming from this finite Markov chain, what does a stationary distribution look like? What is the mixing time? Emphasis on the first question. So Greg, together with Bramson and Griffith in 92, proved convergence of the IDLA cluster to the ball when rescaled. The error bounds were improved first by Greg, and much later, after a lot of attempts by other people, in 2 works, one by David Jerison, Lionel Levine, and Scott Sheffield, and another by Essela and Godelier, 2 independent works, showed that in fact the fluctuations are logarithmic in 2 dimensions and even smaller in higher dimensions. Another area where this was taken further is starting not at a point source but at multiple sources. For instance, if we start at 2 points, we get this type of red set, and in Lionel Levine's thesis done with me, we've investigated quite diverse starting measures. Now we're going to go back to the erosion model, but what graphs will we study it on? Well, mostly discretizations of planar domains. So we start with a planar domain, draw a fine lattice inside, much finer than this one you can see, and we have this blue source and red source which alternately emit particles. What's not colored in is all the vertices inside are colored. So some are blue, some are red, a fixed proportion, not necessarily half-half. So just some fixed number are blue, some fixed number are red, and that fixed number will be retained throughout the process, as I mentioned. Okay, so and then the question is, how does the blue region look after running for long enough? And now maybe we can go back to that video, and now it will make more sense. So here, sorry, this video could still be improved, but it shows you some snapshots.
You start from a random configuration there?
Okay, so the initial configuration was random but not half-half, so the proportion of blues is only 1/3, and you're not really seeing the full evolution, just some snapshots along the way. And by this time, it's roughly reached stationarity, so there are still fluctuations as the blues get emitted and the reds get emitted, but it's quite remarkable how a clear interface emerges. Well, maybe less remarkable for those experienced with IDLA, but otherwise, we start with a mess of blues and reds, and there isn't even any kind of dust of blue inside the red region and dust of red inside the blue region. So this kind of behavior, which we see, is it's very clear that there is an interface here. You can, from the picture, already guess what it is. It's a circular arc orthogonal to the boundary, so it's a hyperbolic geodesic. And and although there are some fluctuations near the boundary, there are no exceptions far from the boundary. Not a single red cannot survive in the blue sea. So this is something we observe. What we can prove is a weaker version of this picture, namely we'll see a statistical version of what you see in the picture, which will appear in our theorem. Okay.
That was 1/3, 2/3?
Yes, 1/3, 2/3. Yes. So if you do half-half, of course you'll get a diameter which is not surprising. If you do 1/3, 2/3, you might think, well, is it a straight line or a circle? It's not a straight line. It is a circular arc. That's why we didn't do it 1/2, 1/2. Okay. So this was the kind of a snapshot of the stationary distribution. Okay, now what happens in general domains? And the point is that this is there is some conformal invariance here. So you have a blue source, a red source. You fix proportions, then you'll get an interface which is a conformal image of this circular arc. One thing to be careful with is that I'll come back to this, is the conformal map does not preserve volumes. So even if you start with 1/3, 2/3 here, it will correspond to some picture like this here, but not with the same proportions. So one can calculate what are the resulting proportions, but they're not equal to what you started with. The main result confirms this, although much remains to be done. We have various technical assumptions, like we need the boundary to be exceedingly smooth. It shouldn't really be needed. It should be much more general. So we have a theorem in this direction, but there's lots of room for improvement. With these technical assumptions made it much easier, so the proof is only 50 pages. But but it's possible that there is a easier way to handle things. So our setup is, again, for technical reasons, instead of starting at a single point here and a single point there, we're going to start in little disks. So a little blue disk, a little red disk. We're going to start uniformly in the lattice points in this disk, and as we scale the lattice size to 0, we're also going to more slowly decrease these disks so they converge to point sources. Again, the theorem should be true starting from a point source in the lattice, but it's technically easier to handle this case. Okay, so we first send the mesh size to 0 and then send the delta, the radius of these disks, to 0. Okay, so we're going to consider domains, but not completely general ones. Will require analytic boundary, which is a real analytic boundary, which is equivalent to having the conformal mapping from this domain to that one extend across the boundary. Okay, so this is restrictive assumption on the smoothness of this domain that we are mapping to. Okay, so we'll have to be careful about which conformal maps we choose, because there isn't a unique choice. We are already fixing all but one degree of freedom. We're going to have the two sources, x1 and x2, the limiting sources at the boundary, being mapped to -I and I respectively. the remaining degree of freedom will be needed to control the volumes. Okay, so the orthogonal circular arcs in the disk can be written explicitly in this form. Log of z minus I over z plus I is a constant. And so if psi is a conformal mapping, then we can define domains u beta, subdomains of the domain of interest u, using the conformal map C and these circular arcs. Okay, so here we have u beta, and it's mapped to a domain d beta. Now, suppose we're given a proportion alpha of blue particles that we want in the domain u. Then we're going to choose which u beta are we going to choose. It's going to be the one. So we're going to fix the parameter beta so that the fraction of the area contained in u beta is alpha, and that will be u parenthesis alpha will be the u beta where beta is chosen, so that this has fraction alpha of the area. So as beta goes from 0 to 1, you scan through all possible area fractions, so there is unique such beta, and this u alpha is not mapped to d alpha by psi because these conformal maps, as I said, don't preserve area. So here is the formal statement of the theorem. So given the blue set in the lattice, so we take a fine lattice. This is the blue set in the stationary distribution. So it's a random set in the lattice. Now, we create from it a random set in the continuum by just surrounding every lattice point by a little square. And this is this set blue square. And then our theorem is that if you look at the difference, symmetric difference of the filled-in blue set with this domain u alpha, again, when we start with proportion alpha of blue particles, then the expected area of the symmetric difference goes to 0 when you first let the lattice size go to 0. So n is the parameter determining, so the lattice size will be 1 over n, and then let delta, the size of the initial sources, go to 0 as well. So again, for technical reasons, it's easier to handle n that goes to infinity along powers of 2. And so this is a theorem in the direction saying convergence to u alpha, but it's not the strongest of this type. So this is statistical convergence, or convergence of empirical distributions. So this theorem, again, let me go back to the same, it doesn't exclude small dust. So if we had like a single or a small number of blue particles deep inside the red region, they would not violate this theorem, because this says that just most particles on the side that's supposed to be red are indeed red, and most are on the side that's blue are indeed blue. The stronger theorem we'd like, which I'll mention at the end, we do have in some special cases, but not in general, is that you have this interface, and the stationary distribution is pure outside the small neighborhood of the interface. Okay? So that's the stronger theorem, saying that there's a small negligible area boundary of the interface, where outside it everything is pure. The red side is completely red, the blue side is completely blue. We don't have that at present in general. We just have a statistical statement saying that that the area of exceptions goes to 0.
So these random walks are doing reflected random walks?
They're doing reflected random walk, yes.
I can't see why you can't start them all with one little source on the boundary.
You can. It's just of course, you can start them all at one little source of the boundary, and it will be the same result. For technical reasons, it's easier to prove in this version, but there shouldn't be no difference. So let me say that okay, I'll sketch some of the arguments, but once there is a clear interface, then it's very easy to convince yourself what the interface should be. The problem is that when you initialize the process, sometimes, initially there is no interface. The red and blue can be a jumble, and that's where these technical assumptions become most convenient. So, you have to worry about very strange initial configurations where which are much stranger than this. I'll give you some examples where the red really encroaches very close to the blue source, and if that blue source is a point, those cause some technical difficulties. Okay, so let's first get the heuristic. And so suppose there indeed is an interface between the red and the blue. What should this interface look like? So it's easy to realize that the interface should have the property that harmonic measure from both sides should be the same, except for having, if you think of it as having a direction, it should have opposite direction, but as a measure on the boundary it should be the same. Because if, for instance, if this segment has a higher measure from the blue source than from the red source, then since we alternate fairly, it will be pushed upwards, and so this won't be a stable interface. And let's see, where is the chalk? Now, you may already know that the circular arcs have this property, but one way to see it is, it's clear if you have exactly a diameter and you have a blue source here and a red source here, then obviously by symmetry the harmonic measure on both sides here is the same. Now if you apply a Möbius transformation that takes this to a domain like that, right, mapping this diameter to this circular arc, then it's a conformal mapping of the whole disk. It should preserve harmonic measure in both domains. So since the harmonic measure here was equal from both sides, right? If we take any segment here, its harmonic measure is equal for both sides. It must also be true here that any segment has equal harmonic measure from both sides. Okay, so again, geodesics, hyperbolic geodesics have this property of equal harmonic measure. And besides characterizing stability, we can again see the direction of the instability. So here is some interface which, suppose it's momentarily deviates from this geodesic, then you can see that this red interval, its red harmonic measure is going to be higher than the harmonic measure of this arc, because random walk particle, in order to hit this circular arc, it must go through this red curve, but not the other way. So this red arc has higher red harmonic measure than the one for the circular arc. On the other hand, it has smaller blue harmonic measure, so it's pushed down. Similar logic shows that this one has higher blue harmonic measure than red harmonic measure, so it's pushed up. So not only is the circular arc kind of a fixed point of these pushes, but when you deviate, you get pushed towards this interface. Because this is all very intuitive and simple. The problem with the model is that initially and for a long time, there's no clear interface. It's just a jumble of blues and reds. So that's kind of what you have to deal with. And you start with this: where is the interface? So we still are motivated by the idea of the interface, but we have to do some more work. So the content of the theorem can be restated as follows. So if omega epsilon's configurations with less than epsilon n squared, right? So when we divide in n by n, we have order n squared vertices altogether. So look at omega epsilon, which are configurations that have less than epsilon n squared vertices with the wrong color. So Wrong here means separated by the geodesic from their corresponding source. So this is an example of such a configuration, which is for a small but not tiny epsilon. It's still in omega epsilon. Most vertices are well behaved. They have the right color, the same as the corresponding source. But you have occasional exceptions. Their total mass is less than epsilon. Okay, so such configurations we never see in real life in simulations, but for the purpose of the theorem, we still count them as okay. And what we want to rule out is just having a higher proportion of blues in the red region and vice versa. Okay, so omega epsilon has the property that the area of the symmetric difference of the blues and this region below the geodesic is less than epsilon. And one more formal statement of the theorem is that if the size of the sources is small enough, this delta 0, and the lattice is fine enough, this n that defines the lattice mesh is 1 over n, n is large enough, then the stationary measure, remember we have a Markov chain here, and the stationary measure of omega epsilon is very close to 1. So with an exponentially small error in the volume. So once you have that, it's easy to get the main result in the previous formulation with the limits. So in order to prove this, we're going to use a Lyapunov function that is a function which always increases when we are outside our target set omega epsilon. Increases in expectation, I should say, so it will give us a sub-martingale, and hence it will attain its maximum in omega epsilon. Okay, so we start from some initial configuration sigma 0. So although the result is, as stated, is about equilibrium, we're going to prove it by actually starting from a completely general configuration, bounding the time that it gets into omega epsilon. So, and then showing that once you get inside omega epsilon, or actually deep inside omega epsilon, so say inside omega epsilon squared, then you will stay in omega epsilon for a very long time. Because the stationary distribution represents the asymptotic fraction of time you spend in different regimes, this will be enough to control the stationary distribution, but also gives you additional information, because it's not just about stationarity, it's also about the convergence. So the key thing we need to start with that is to find a function, as I said, with this growth. So if we start in sigma 0, which is outside omega epsilon, we want this function to grow. On the other hand, it will be bounded, so this will force convergence to omega epsilon. And the basis of this will be to build the Lyapunov function. We'll use the dipole green function. So because we have a reflected random walk, the green function from a single source is not naturally defined unless you do some truncation. But once we have two sources that balance each other, then there is a natural green function. So this is a function whose Laplacian will be 1 on the blue source and minus 1 on the red source, and it can be constructed in terms of the random walk up to a constant by the following procedure. So I'm going to run a random walk, and it's convenient sometimes to run discrete time, sometimes to run a continuous time walk. It really makes no difference. So here I'm using the continuous time notation, but you could also do a sum over discrete time. So here we're measuring the time, the total time starting from location x of a random walk, how long it spends in the blue source compared to how long it spends in the red source. Again, each of these integrals by itself would of course diverge, but when we subtract, because the size of the red and the blue source is identical, then the difference between these probabilities goes down to 0 exponentially in time, with some parameters that depend on n and so on, but there's certainly the difference decays fast enough in t that this integral does converge, and will give you this dipole green function in the discrete world. In the continuous world, you can write it explicitly, as I'll come to. Now here's some further heuristic that why the interface, once it exists, will be a level set of this dipole green function. So we can compare this dipole green function to two classical Dirichlet green functions, one which one for a particle that gets killed when it exits this interface from the blue side, so when it enters the red side, and another and a similar one for the red side. So we have these two natural green functions that have, again, Neumann boundary conditions on the original boundary, so reflecting at the original boundary but getting killed at the interface. And then each of these functions is harmonic, so the blue-green function has, Laplacian 1 inside the blue source, 0 everywhere else, but of course, the normal derivative at the boundary is going to be the harmonic measure. And similarly, the normal derivative of the red function here will be the harmonic measure. So the equality of these harmonic measures means that Gn, if we compare it to the difference of these two Dirichlet green functions, the difference will be harmonic everywhere. But harmonic everywhere with reflecting boundary conditions means it's a constant. So Gn is the difference of these two Dirichlet green functions with respect to the unknown interface that we're trying to find. So this difference is a constant, but now if we examine this along the interface, then each of these functions, the blue-green function and the red-green function, have to vanish on the interface. So what this means is that our stable interface, where we want the harmonic measure to be equal from both sides, must be a level set of the dipole green function, which is something you can kind of heuristically realize in many ways. Again, so then the blue region will just be everywhere where the green function, the dipole green function, is bigger than some constant. Again, this is once we have an interface, and as I said, the technical difficulty is how to deal with the initial configurations that don't have an interface. Anyway, with all that as motivation, we use the Lyapunov function. So given any coloring of red and blue of the vertices inside, we just sum over all the blue locations Gn of x. So remember, Gn is this dipole green function.
Excuse me, but is this using the interface from a particular configuration or for the expected limiting configuration?
Okay. I was jumping between a heuristic and now this is kind of part of the formal proof. So this argument concerned, we're trying to again to understand this interface for the limiting configuration.
Right.
So for the limiting, what?
Sorry, okay, right.
So for the limiting configuration, we're trying to understand what is this interface. Gn is the dipole green function for the whole domain. Okay, and this is G for blue and red. So again, this is part of the heuristic understanding what this interface should be in a different way.
Just the dipole green function on the graph. Yeah. Okay.
Gn is just a dipole green function on the graph.
Okay. Yeah. Sorry.
Okay, so now this will be the Lyapunov function we'll use, and again, what we need to show is indeed this Lyapunov condition that it increases as along the dynamics. So of course, if it increases outside omega epsilon, and you converge to omega epsilon, then W must be maximized inside omega epsilon. So this is a weaker statement than this, but it, in the proof we first prove this this statement. Now, in relating the graph dipole, the Greenian dipole function in the graph to the classical one in the continuum, we're using we need these estimates not just in convergence form, which are kind of classical, but with the quantitative bounds, and conveniently for us such bounds appear in some recent work of Zhenqing Chen and his student Fan, actually related to older work of Birdsey and Chen. But so this is a convenient way for us to handle the quantitative aspects of the convergence, which are in the paper. You can see them on the archive. I won't enter these quantitative aspects here, but just mention that in the continuum, the dipole Green function up to constant has a very simple form, because in the disk it just is log of z minus I over z plus I. So with the conformal mapping, it just has this form. And so what we want to show is with suitable what we need is the fact that with suitable normalization, the dipole Green function in the graph is converging fast enough to this limiting expression. So, what underlies this is that the reflected Brownian motion heat kernel is a fundamental solution to the Neumann problem. So, okay, so once you know that, it's easy to see that the maximum of this Lyapunov function has to be inside omega epsilon. So this is the picture. Gn big, because the Green function is close in the graph, is close to the Green function in the continuum, these domains Gn bigger than beta and Gn less than beta are just separated by one of these hyperbolic geodesics, or conformal images of hyperbolic geodesics. So if you have if you're summing Gn and you want to maximize the value, you will just take everything above a level set in order to maximize the value, since the number of blues is fixed, right? The number of blue particles is fixed. We want to choose a set of exactly k, which is a proportion alpha of the volume, exactly k blue vertices. To maximize the sum of Gn, the best choice is everything above a level set. And so this choice is in omega epsilon. There are very few, in any such maximizing choice, there are very few blues on the red side and reds on the blue side. Actually, verifying the drift condition is more delicate, and I'll just be able to sketch a few ideas in that. So one step of the dynamics is remember, a blue particle emits from the blue source and reaches the first red vertex, then that's a new blue, and here's a new red. So the difference in the W between the new configuration and the old configuration is just Gn of the new blue minus Gn of the new red, because remember, the Lyapunov function, we summed the dipole Green function over all blue vertices. So we gained the blue vertex because of this move, but we lost the blue vertex because of that move. So this is the difference in the value of W. So difference of Gn between these two values. So really what we want is to say that when we start outside omega epsilon, the expected value of this difference is positive. So the new blue is going to be created closer to the blue source in this metric measured by the dipole Green function than the blue particle that will be lost to this red source. So really this analysis is based on analyzing many different, at least the way our current understanding goes, the intuition was very clear about a year and a half ago, and actually pinning down all the possible cases rigorously took quite some time and effort. And so, as I said, in general, there's no interface. There are two natural interfaces that you can always define, namely, if you look at the red source, you can look at all locations that are reachable from the red source while staying by purely red paths, right? So if you have some domain, here's the red source, you can look at everywhere you can reach by purely red paths. And similarly, from the blue source, you can look at everywhere you can reach by purely blue paths. So, and then look at the boundary of these two regions. So that gives you two kind of potential interfaces. And your new particles are going to be on the boundaries of these interfaces. These interfaces could be far apart, and also, so if I look at where this is, okay, so this will say this is the blue and this is the red. So if I look at everywhere that the blue can reach, of course it can surround some red islands. So we have to, but we can look at the outer boundary here, the outer boundary here. These are two disjoint domains with different, possibly overlapping interfaces, and with holes. So the key estimate, which is used in the proof, is an estimate that relates the change in the green function, the change in our Lyapunov function, to effective resistances. And this picture is a little misleading, really. So we have blue source here, a red source here. Here I just drew one interface, but really you should think of both interfaces. So the blue into the boundary of everything reachable from the blue, the boundary of everything reachable from the red. And then there is an effective resistance from the blue source to the boundary of this blue region, to the blue interface, and similarly an effective resistance from the red source to the boundary of the red region. And kind of a key potential theory estimate that gets used is that the difference in the value of the Lyapunov function in one step, the expected difference, can be written as a difference of effective resistances. So this is the effective resistance from the blue source to the red source in the graph. So this doesn't depend on the current configuration of particles at all. This is a constant. But we have to compare it to a sum of two things: the effective resistance from the blue source to the kind of boundary of the blue interface, and from the red source to the boundary of the red interface. So this kind of a key calculation, which just takes about a page of calculation in the paper. It's not very hard, and there's a kind of negligible error due to possible overlapping of these interfaces. And once you have this form, then you see that that this should always be non-negative, because the right-hand side is what you get if you glue everything between the blue and the red interfaces. So, and gluing always with this, so this will be, so this difference we subtracted, what's in the square brackets, is also the resistance from the red to the blue sources, but when we glue everything between the red and the blue interfaces. And gluing always reduces effective resistance. What we then have to show, it's not enough to have this non-negative, we want a positive gain of the Lyapunov function, and that's where we use the condition that we are outside omega epsilon. Once we have enough blue particles on the red side or red on the blue side, then this gluing will actually reduce the effective resistance by a measurable, strictly positive amount, and that's the so again, to really prove this, you have to consider two different cases. So here we're looking at, so this is the blue interface. Remember, it's everywhere you can reach from the blue source while staying purely in blue. So look at this blue interface and consider two cases which cover kind of most possibilities. So remember, we assume we are outside omega epsilon, so we have a large fraction, say, of blue particles in the red region. What could cause this? So one possibility is that this blue interface is very far from these hyperbolic geodesics. It doesn't correspond to any hyperbolic geodesic. So, so what it means is that if we look at the dipole Green function evaluated along this blue interface, it varies a lot. And when the potential varies a lot along the interface, and now we take this whole interface and glue it together, this reduces the effective resistance substantially. So that's what happens in this case. Another possibility is that this blue interface actually is close to one of these geodesics. So why, in that case, why are we not in omega epsilon? It's because this interface is violated by, so there are big holes, say, either reds in the blue region or blues in the red region, which bring us outside omega epsilon. And again, in these cases, these holes, since we assume their total mass is bigger than epsilon n squared, they are large enough, so just their gluing is going to reduce the effective resistance by a substantial amount. So they need not look like this at all. So they could be, there could be a lot of sprinkled dust here. But still, there's a lot of them. So these exceptions are epsilon n squared. So they cannot all lie on one level line. They have to lie on different level lines. And so gluing them together reduces effective resistance by a substantial amount. And so as I said, Rayleigh monotonicity principle gives you that this, together with a quantitative version of the monotonicity principle, gives you a positive gain in this difference, and so gives the Lyapunov condition. Once we're there, the rest is much easier. We can then use the Lyapunov function to find that the heating time of omega epsilon will be order n squared with high probability, no matter where we start, just using the fact that this Lyapunov function keeps increasing. And so starting from any coloring, the process hits omega epsilon quickly. On the other hand, if we are in omega epsilon prime for suitably small epsilon prime, again, we will also hit omega epsilon prime quickly. But then another estimate we make is that once you start in omega epsilon prime, well, you might be exactly on the boundary of, so by the way, this picture, this is not the domain. This is an abstract picture of the state space. So this is some space of size exponential in n squared, and this is just showing kind of the behavior of our Markov chain on colorings. Right, so once this Markov chain on coloring hits the region omega epsilon prime, then again one can use this Lyapunov function with the drift it entails to show that takes you a very long time to exit omega epsilon. So the probability that you exit omega epsilon in less than exponential time, exponential in n squared, is exponentially small if you choose these c's small enough. So it's
doesn't this contradict your previous result?
No. Again, the previous result says that I hit omega epsilon quickly, and just by changing epsilon, I hit omega epsilon prime quickly. Okay. Think of so the naive picture is, think of a biased random walk, say with bias in this direction. Right, such a biased random walk, wherever you start, so suppose you have some long interval, wherever you start, you quickly head in this direction. But once you're, say, in this region and the bias is to the left, you have a reflecting barrier here. Still, it will take you a very long time to, say, exit a larger interval because you're going against the bias. This is the same picture we're talking about here. You have a strong drift towards omega epsilon prime. So remember, omega epsilon prime is where there are fewer than epsilon prime n squared exceptions to the color rule. Once you are there, you have some fluctuation, but to have a larger number of exceptions, a much larger number of exceptions, will take you a very long time because that's what's going against the drift. Okay, the drift all the time tends to reduce the number of exceptions, but the problem is the drift gets weaker and weaker as the number of exceptions decreases. So
Intuitively, this makes me think you should have enough time to fill up those little holes.
I'm absolutely sure you should have enough time. Maybe we didn't have enough time to verify that the process has enough time, but so there's no doubt that you fill in the holes, and our feeling is just like yours, that there are enough elements here to prove it, okay, so there is something definitely left to do here, which looks accessible. And of course, once you have these kind of strong estimates on heating times, then you can use the description of stationary measure as ratio of times to get the facts about the stationary measure. So we get this strong statement. Well, strong about omega. It's weak because it only concerns omega epsilon. It's strong in that we have exponential control of the measure of the complement of omega epsilon. So the main result, as stated, we don't yet rule out this existence of this dust, although it's definitely not there. Let me say that in a special case, we have done that. So that's in a related joint paper with Shirshendu, but with Lionel and Jim Prof. We consider the easier case where everything happens on a cylinder. So here I've unwrapped the cylinder, but consider just a lattice drawn on a cylinder where the blue source is just the bottom circle, the red source is the top circle. Okay, now you again alternate moves as before, and now it's clear what is going to be the interface. It's going to be some intermediate height circle, and so here the Lyapunov function is rather straightforward. It's just the say the total height of the of the red particles. So that's going to grow all the time, and because of the simplicity of the Lyapunov function in this case, so there's no convergence difficulties to the dipole green function. Then here it's easier to go all the way and show there are no exceptions, no dust particles. So we have the interface and a small interval around that. Except for a small interval around the circular interface, there are no exceptions in this case. So, and that depends on precise IDLA estimates going back to Greg's work and the more recent work of Jerison, Levine, and Sheffield. So, some things that remain to be done, almost at the last slide, is rule out the dust particles. So there's, that looks close, but we haven't finished it. Find the order of fluctuations. So this argument, as I wrote it down, it just showed, that this epsilon goes to 0, but one could get some rates from it. They're very far from sharp, so getting good rates, probably it makes sense to first do question 1 and then get rates for the fluctuations from the interface in that stronger sense. Again, one can ask the same question in higher dimensions, and it seems clear that again in higher dimensions you can always define the dipole green function, and it should be level set of that dipole green function. Again, there are more technicalities because interfaces in higher dimensions can be more complicated. It's very easy to guess the result. Proving will involve quite a bit of work. A strange model, sorry I didn't bring a movie of it, is when particles are released in the same location. So the red and the blue source are actually the same. So you alternate releases from the blue and the red source, but otherwise the rules are as I described them. And then this picture grows much more slowly because, you know, a blue particle emerges from the source and goes somewhere. Then a red particle emerges. It's very likely to just cancel the effect of this blue source. So the actual growth of the shape is quite slow. And we just have really nice simulations of this, which I'm sorry didn't bring the movie, but this is just some snapshots from how the process looks. There's a lot of swirling, so proving anything about this is a challenge. The behavior with more colors is quite intriguing because except when you have equal numbers, it's not clear what the interface should be. By the way, here to have preservation of mass, you have to be careful. If you just go round robin, you know, blue particle, green particle, red particle, and so on, then even if you start with a very small proportion of greens compared to the others, say, you'll get equalization. There will be drift towards the center. So to get preservation of mass, you have to do something different. So you can have, say, a green particle gets emitted, and if it, say, swallowed a red location, then the red gets the next turn, and so on. So that will keep the balance. And then what will the shape look like if you don't start with 1/3, 1/3, 1/3? What's the characterization of it is we don't know. And yeah, that's almost all. And that's it. Thank you.
We have time for some questions, if there are some.
You said that in the case of three colors, you don't know what the asymptotic shape is.
Right.
Do you have any conjecture?
No.
And my other question is, are there other competitive or other models with competition of two species or populations where you expect similar behavior as in normal?
So, you know, this famous model of competition is the first passage percolation competition, and there one doesn't expect this this behavior. But if you do a model where you have first passage percolation, but the transition time is 0 with probability very close to PC and positive on the other case, then it's known that, you know, first passage percolation generates a shape which looks more circular or converges to conformal invariant. So if you use this rule, so then the passage time is 0 with very high probability, PC minus epsilon, okay, and say 1 with the remaining possibility. So then you get a process which is approaching criticality, so it should approach conformal invariance. So that kind of competition, so you have two sources, they both perform first passage percolation and conquer, you know, every vertex gets conquered by whichever color reached it first. Then one might expect a similar behavior. This has been simulated a lot in the one color version, but we haven't simulated it in the two color, but that's a place where I would expect similar behavior.
Two questions. The first one is, I mean, at the beginning there's this problem with the reflected Green's function, which we all, you know, struggle with. So if you were to take a discrete torus, you know,
yes,
like a bit like you did with the cylinder, and have 2 points there, then you kick out that problem. So, but you will still end up with the same questions with the islands and dust as in the end, right? I mean, somehow or would that actually simplify something all the way through? Basically, you know, you would have just a level line.
So that's so it removes some complication.
Log singularities on
Right. So in the model as I described, there are two really kind of sources of complication. One was the boundary reflection, and the other is the fact that the approximation of the discrete dipole function by the continuous dipole function. And both of these cause some pain in getting an exact result with a dust-free result. So we have, so we thought about the version you mentioned. We didn't analyze it in detail because we just did the two extreme ones. The one I described in the talk, which, where we address both difficulties, obtaining a weaker result with dust, and the one in the cylinder where really both problems go away. The green function is just, the dipole green function is the same at all scales. There's no approximation. So you can, and even that case, I was surprised because initially we thought of including that case in the main paper as like a little warm-up, but that warm-up grew and grew, and it's like, I'm still shocked that it takes 30 pages to explain that very simple case in full detail. It doesn't seem to me like it has to be that case, but we haven't found something simpler.
My other question is, do you understand it correctly that if you would start, say, with a configuration where a given subpart of your all eventually piece that is going to be all red, I mean, some neighborhood of your red source is actually completely red.
Uh-huh.
Do you understand correctly that somehow what you're going, you still get the idea that your convergence result will probably hold before anything in that red subregion gets.
Right.
There will, I mean, you can't create dust in a place.
That's right. So part of our estimates, which I didn't go into, show that we can rule out dust close to the sources, close to the source. So so each source does have some territorial waters where it completely can stamp out the dust. This comes back to also to Greg's question. So yes, the estimates are good enough for that. The problem is if you have, quite close but still macroscopic distance to the interface, there is difficulties because of rates of convergence issues of the stationary measure to the limit. So ruling out dust can be done close to the sources, just at medium distance, relatively closer to the interface than the sources is still some difficulties.
Greg,
This
one more
was
question.
related to this question. I mean, I asked the analyticity of the boundary assumption. Was that just for the discrete Green's function?
That's the main place, but once we needed it, once we assumed it, it simplified many of the technical arguments in cases I didn't even go into, where the configuration just looks locally nasty. The analytic boundary made things easier, but in a way which could easily be circumvented, adding a page here, a page there.
I propose there are many questions, but we have to go on. In 5 minutes we start the next talk. So there is 5 minute break and other questions may be asked after the longer break.